Hi, I'm back for development log number 10 of MegaSplat. So I recently submitted everything here to the asset store. It's waiting approval. This also includes everything from development log number 9, which is also in this next coming release. And so one of the big features here is unification of the shader system so that the terrain system has all the same features that the mesh system does. This is actually really good for me because it unifies a bunch of my code, and so I have less chance of breaking things and more shared code, which is good. So on the terrain painter here, you'll see you have the normal MegaSplat brush. We now have flow, puddles, and dampening tabs. If I want to paint puddles, what I can do is come in here, set my target value to 1, and I have some reasonable brush and flow settings, and I can just paint puddles in as long as my shader has them supported. And then I can go to the flow direction here and paint some flow to get them moving in the direction I want. All the features that Mesh has had are now working for terrain, and everything's unified, which is awesome because it means that all of the interesting effects that I've been working on for meshes are now working for this as well. Another big feature that was added is an example of runtime painting. So I'm going to go ahead and hit play here. And what we'll see is this guy, as it moves across the terrain here, it's actually changing the terrain at runtime. This works for both meshes and terrains. It gives you a good idea of how to do runtime modifications to things. So I do want to discuss the code of that just a little bit. So if we go to the examples folder and we go to the runtime painting code and bring that up, what you'll see here is that this is heavily commented code because it's an example for you guys to use. There's a bunch of hackery I have to do to restore the terrain when you're editing. None of this is really necessary for runtime, but what happens is the texture on a terrain stays around in memory between play mode. It does not get reloaded, and so then your painting at runtime stays around in your editor. Even though on disk, it's still the original thing that you had. So I had to figure out some ways to restore this. So you'll see a bunch of this stuff for the terrains to restore it. For the vertex data, it's much simpler. For painting into the terrain data, it's pretty much just editing the texture. There's not a whole lot to that. But what there is for meshes is a lot of room for optimizations versus sort of a trivial implementation. So what I do here is I raycast into the terrain, and if I hit it, and if I have terrain, I'm going to call it paint terrain function. But if I have a mesh and it has a vertex instance stream on it, then basically what I'm going to do is modify those vertices. So the meshes for these landscapes that I've made have about 32,000 vertices in them. So going through those and doing distance checks to them all can be quite expensive. Now you could go the route of having some sort of spatial hash. Now the way I would consider doing that is by reordering the vertices such that I know that vertex 0 through 1,000 is in this quadrant, and from 1,000 to 2,000 or whatever the numbers end up being is in this other quadrant. And so then I could very quickly get to a chunk of vertices that I'm most likely colliding with. But before I do anything complex like that, whenever I'm working on code, I like to see if I can make just the simplest method go as fast as possible, because then if I add a complex algorithm, it will not only be faster, but I may not need to write that complex caching mechanism for, like, in this case, some sort of spatial hash. So I found that I could actually get this really fast by doing a few things. So once we realize that we're going to paint on this thing, we basically need to get some data from it. And the first thing I do is actually just cache those arrays from the vertex instance stream locally. This is a very minor speed up, but it does make a difference. Just having things as local variables versus fetching them from the external component each time is much faster. And then I can look at the component that I've written here has a question of, like, do I paint on the top layer? And so to paint on the top layer, you really need to have UV3 because that's where it's stored. So I'll just early out if it doesn't for some reason. And then what I do is convert the collision point into the local space of the mesh. And so that's so that you can do your checks without having to convert each vertex into the world space each time. So essentially I do one matrix multiply versus one for each vertex. And what you'll see here is that I pre-multiply this BZ value here is the scale times the brush size. So that's basically how we do our basic, am I within distance of the brush? And then I square that, and that's so that my distance check does not have to do a square root. That's a very common optimization. And then, because vector math is particularly slow in Unity, I go ahead and take everything out of my point and make it just floats. So you might not think that calling vector3 distance or some vector3 multiply would be slow, but it actually is significantly slower if you have an inner loop like this. I wouldn't do this everywhere, but for an inner loop that you're going to do 32,000 times in a frame, it's probably worth it. So finally, we get the texture index, which is again just whatever value you set divided by 255. And then we just loop through the vertices. I cache the length so that we don't have to fetch it from the positions array each time. And then here, really what I'm doing just here is a vector3 distance, but I've unrolled that. So I take my my vector3 and I go ahead, I subtract off the the vertex position from my hit position in world space, in the mesh space. And then I do the actual distance calculation without the square root because we've already pre-squared the distance. And if it's within that range, then I know I'm in the range of the brush. So this actually sped up things by an order of magnitude, effectively, by just pre-multiplying this to get rid of the square root and not using any of the vector3 functions. It's extremely fast comparatively. And then if I'm within the fall-off range, then essentially I compute my brush fall off and my final strength, and then if after the fall off, because the brush is a sphere, the vert still qualifies because it may not actually change it. If it still is going to be changed, then I go ahead and change it. And here's actually where we do the change. So what we do is we grab the vector 4 from the UV3 arrange, if we're painting on the top layer, that is. We set the texture index on the W channel there, and that's just that value divided by 255. And then here we just lerp the weight for the blend weight between the two layers. We lerp that towards our final target weight, essentially. And rather than calling into mathf lerp, I unrolled lerp into the actual lerp equation. So there's something I should probably say about mathf and the vector3 math is that most of it will convert into doubles and then convert back to float. Now, I've heard that on 64-bit architectures working with doubles is faster, but casting from float to doubles and then back again seems to me like it would end up slower. I have not tested that because I'm not going to rewrite mathf to be a float-based version, but usually just unrolling this so you don't get the function call overhead and then keeping it all in float space tends to be a lot faster. So all in all, this sped up this process. Originally, when I was painting over 32,000 vertex mesh, it was about 2.5 milliseconds on my machine, and this gets it down to like 0.2. So it's literally 10 times faster from just unrolling a few of the math operations that we normally use. And again, because you could actually go look at what this library is, see what the actual code for it is. You can look it up in a number of places. So it's not that hard to unroll some of these in inner loops. And then finally, if I actually changed this mesh, I'm going to call stream apply, and I'm going to pass false. What this does is apply can say, look, I don't want to make this readable on the CPU anymore, so upload this mesh and forget it. We don't want to do that because we're going to change it the next frame too. So then we apply the stream, and that's going to update the vertices on the actual GPU, and it'll all update. Paint terrain is very similar, just a lot simpler. Again, I unroll and pre-multiply. I do the squaring of the brush distance, so I don't have to do the square root from the distance check, and then I unroll these loops and roll a lot of the math. And essentially that speeds this up considerably. And then instead of working with vertices, I'm working with a texture. So I have a color value here that I get pixel on, and then I set the texture and set the weight, or set the other texture and the weight and set the pixel back. And then when it's changed, I actually call apply. So it's pretty straightforward. If you have questions about why I've done things certain ways, please feel free to ask. Or if you have other optimization ideas, feel free to try them out, profile them, and let me know, and I'd be glad to integrate them in. Overall, painting painting on a terrain is really fast. Painting on a really high poly mesh is still reasonably fast. Certainly fast enough if you're not trying to paint, hundreds of thousands of verts every frame. If you're only painting one mesh at a time, it's fast enough for most games. So that's painting on meshes in real time. There's one more thing I'm going to show off, and let me just load a different example scene. Actually, that. Let's go grab the mesh scene here. So here we have our, low end or mid range or whatever, just basic mesh scene. One of the things that's really annoying is if you want to use light mapping or static batching, then you would have to select each one of these meshes, and you'd open up the Vertex Painter Pro, and you would go to the Utilities panel, and you would bake this actual mesh out with Save Mesh, right? And then you'd replace the mesh in here, and then you'd be able to mark it as static. Well, that's a lot of work, especially if you have a lot of meshes. What there is instead now is this bake scene to mesh cache. And so what this does is say, take everything under my selection, or if you are putting this into a batch process, which you can do as part of your build step, find all the vertex instance streams, pass them to this function, and then what I'll do is I'll take all those meshes, I will save them out to one asset file on disk, which I call a mesh cache, and replace them all in the scene and mark them static. And so here we can do a manual version of this, and let me just save this scene somewhere else. And I actually already have some testing here. Here's my mesh bake scene. Place. And so here we'll see on a terrain painter we have the vertex instance stream down here, right here. And I have a little checkbox on here called Keep Runtime Data. So if you set this to true, then what's going to happen is that the runtime data needed for painting is going to be stored on here. I forgot to mention this in the last thing. So if you're doing painting, that's really useful. In our case, we're going to get rid of the vertex instance stream. So if you bake all your meshes to static and do light mapping, you can't runtime modify them because the static optimizations that Unity does means you cannot edit them on the CPU anymore. So unfortunately, there's not a way in Unity to have static meshes that you could modify because they're static, right? So that's what that is about. I forgot to mention that in the last part of this video. So hopefully you kept watching. But we have a MegaSplat collision info on here, which is what allows us to query for collision queries and things like that. It will, when we bake this scene down, it's going to rip off all these vertex instance streams, and then the MegaSplat collision info is going to cache all the data needed for its uses. This is like the physics interactions and for knowing what texture you're stepping on, etc. So that you can still use that stuff, even though you no longer have the mesh on the CPU. So it'll cache it off for you. And so that's really cool. So let's go back to our bake scene to mesh cache here. And I'm going to enable static batching at the end of this. I'm going to keep the mesh editable, which means just keep a copy on the CPU so that you can re-upload it. Now, for light baking perspective, they won't let you do this, but for other reasons, this is useful. And then I'm going to process only the current selection. And I'm going to select the meshes so that we process everything below meshes. And I'm just going to do save and replace. And what this is going to do is it's going to make this mesh cache object with all the burned out meshes. And so you can see now that these have changed to green for their wireframe, which is how Unity tells you that they're static. And so now if I select one of these, you'll notice that the static flag is set. It still has its MegaSplat collision info, but the actual vertex instance stream is gone. There you go. So you'll see that our mesh cache here contains all of the meshes that we baked out for this scene. So you can insert this into your pipeline, and you can do this as part of your build process or your lighting baking process by calling the functions on this tool. They're exposed in a way that makes that easy, and then you can not think about having to save out these meshes and flip static flags anymore. It'll just do it for you. So this has been my update for the week, and I will see you around on the forums. Thank you.